so we are going to do a little bit more integrating. So we're going to do a day 2 for packet 4. So the first thing I want to do is finish going over the mini mock exam. So I want you guys to look at number 6. This actually doesn't have to do with packet 4, but we didn't go over it yet. And there's a question just like this on your quiz over packets 3 and 4. So on number 6, when it's asking you for the maximum value, that's the same thing as absolute. That's where you got to find the critical numbers and you got to test the critical numbers and the endpoints. So I want you to go ahead and check your answer to number 6. Okay, 7 and 8, these are both packet 4 questions. These are integral questions. Now 7 is actually easier because it's asking you to derive the integral. So you actually don't have to do either, right? All you got to do is deal with the bounds. This is called second fundamental theorem of calculus. Okay, and we're going to record that on the green sheet in a minute. So this is when you're deriving and integrating. Those are kind of like canceling each other out. So you're going to plug in your top bound into the function. Notice that I didn't derive the function. I didn't integrate the function. I didn't do either. You plug in the top bound, then you go derivative of the top bound, not the function, but the top bound. Minus, and then you do the same thing with the lower bound. This is called second fundamental theorem of calculus. It's not a big deal if you know the name. You just need to know this is how you do these problems where you're deriving an integral. This is on every AP test I've ever seen. You're going to see this. And it's really easy if you don't make it harder than it needs to be. Okay, number 8 was just a normal integrating problem. You had to integrate each piece, anti-derive, and then you had to plug in your bounds.
On number 6, you just plugged in all those values up into the original alphabet.
Yeah, on number 6, you just plugged in your endpoints and your critical numbers, which one of them ended up being the same. You plug those numbers back into the original. Biggest one is your max. All right, so now I want you to turn to number 15, and this was a Riemann sums question, or sorry, 14. This is a Riemann sums question. It was a trapezoidal sum. Okay, we reviewed that a little bit yesterday. And one thing I want you to notice here is that the time intervals are not equal. A lot of the Riemann sums, you have equal subintervals, but not always. So I want you to notice that I was multiplying by a different amount here. So check your answer with mine. If you didn't get B on 14, then look to see, did you multiply by the correct time difference? And you get that just by subtracting your 2 times. That tells you how much time has elapsed over that subinterval. Okay, if you turn the page and look at 15, this was a free response question. And we had actually seen a lot of these on the after parties this semester, but this is, you're gonna have a table where you're probably gonna have to do a Riemann sum, probably gonna have to explain it, probably gonna have to do average rate of change, maybe average value as well, and maybe even application of mean value theorem, okay, which is where you put average and instantaneous rate of change equal to each other to solve for t. This was a calculator problem though, so although you didn't have to simplify, you could have, and just make sure that your units are correct everywhere. All right, let's look at the next problem. Well, we did 16. Let's look at 17, and then at this point, we've gone over every Riemann sum problem. There is a mistake here, and this was me just not thinking very well. So I'll tell you, my mistake is in D. I want you to see if you can figure out what my mistake was. A lot of you have no idea because you never did this. So you're behind. I just want you to self-assess and understand why some of you feel overwhelmed right now because you haven't put in the little amount of time that I've asked you to put in so far.
You did?
Yeah. Why is my answer wrong? If it's for total distance traveled.
You did everything instead of just the positive.
So I'm going to kind of take what you're saying and tweak it just a little bit. we want everything to be positive. So instead of just adding we want to add these. And if I was just asking for how far is the particle from where it started, I would normally subtract those two because they're underneath the x-axis. But this negative area, so to speak, it's not negative area, but the negativeness of this part of the graph, the particle is still traveling. So we actually need to add everything. So we need to add everything. Yeah, it's like absolute value. So the way this looked like, not when you're given a graph, but an equation, we did the integral of the absolute value of velocity. And we're going to look more at that next week. But I wanted to go ahead and point it out, and I wanted to wrap up the whole mini mock exam thing. So I would have missed points there because I wasn't reading that carefully. I'm not ashamed to admit it. I mean, I am a little ashamed, but I'm just saying, like, you can make little mistakes like that if for the most part you know what you're doing. Okay, you just can't make a lot of them. All right. So now what I would like to do is to kind of fill in some of this stuff we're talking about right here. First of all, just the fundamental theorem of calculus. This is just, I just want to go ahead and put this in. I thought about taking this off the sheet because I feel like you guys know this, but if you are anti-deriving a function, okay, so let's say we anti-derive capital F and we get lowercase f. That was kind of the notation that we used. Which bound are you going to plug in first? The b, okay? So that's kind of why we have it on here. Some people get real used to their calculator and they kind of get the a and b mixed up because of the way we type it in the calculator. Okay, the second fundamental theorem, definitely I want to go over this because this is an easy way for you to get some points without doing a whole lot of work. You're not actually going to do anything different to your function. You're deriving and integrating, so you're essentially doing neither. You still got to plug in the bounds though. See, the upper bound is u. So notice I didn't change this to f prime or capital F. It's the same exact function, but what do I need to multiply this by? U prime, the derivative of the upper bound. Okay, minus, and then you do the same thing with the lower bound. There's another similarity, sometimes it's called a corollary theorem, and notice that the whole deriving and integrating are kind of in a different order, but it's still similar situation. Now a and b here are going to be actual numbers, so we're not going to multiply by their derivatives. Okay, the rest of this we're going to go over next week, okay, which is kind of our last week of like reviewing newer things. And then after that, we'll just go back and review like the things again that we really need and go over the mock exam. All right, I want to work one problem off your packet, and then you're going to have the rest of the time to just kind of work individually. I'll have the key available up here for you to look at, but I would like to look at number 6. Again, it's going to be really difficult for you to just look up here, so hopefully you have that packet 4 in front of you. Because I want to review a U substitution problem, and this is as good as any to look at. We talked about yesterday a problem where it seemed like we were going to do U substitution, but then it ended up not really working. Here, it is going to work, okay, because what are you going to let U equal on this problem? The thing inside the square root. So the thing inside the parentheses, inside the square root, sometimes in the denominator, sometimes the power on e. There were lots of different things, but it was kind of like you're going to let u be part of the problem, and then what we really hope is du then is the other part of the problem. So the derivative here would be negative 2x dx. Normally we would divide out that negative 2, but I want to show you something here. There's actually a 2 right in here, and that means I really don't want to get rid of it. It's going to be less work. The negative, though, I need to divide that to the other side. But see how the 2x and the dx, all of that gets replaced with a du. All right, so here's my big question. What's the power on u if it's in the denominator and underneath the square root? negative 1/2. What else do we need to change in this problem? The bounds. Okay, so if the bounds right now are in terms of x. So what is a 1/2 going to become? It's going to become 1 minus a half squared. Do what you need to do to figure that out. 3/4. Some people are better than others. If this is not a strong suit of yours, you need to go off to the side and do the calculations. Okay, if x is 0, what's 1 minus 0 squared? 1. That's an easier one to do in your head. Okay, now we need to integrate. Okay, so remember, we add 1 to the power, and then we go, and you can do a 1 over 1/2 here, or you could say, well, I know that's going to be 2. That's going to be up to you. So in the end, I do have a negative 2 here. So I'm just going to kind of bring that out to the front. And then I'm going to go 3/4 to the 1/2 power. And before you're like, we don't know how to do that without a calculator. We do. It's going to be okay. And then 1 to the 1/2 power. Yeah. You need to change the bounds when you're doing u. A lot of times, this right here could be your answer, or even just rewriting the integral could be the answer choices. On the next page, I think there's some like that. If you don't change the bounds here, then you can't use u. You got to plug in 1 minus x squared back in place, and then you could use your old bounds. So you just have to be consistent. By changing the bounds, then it kind of keeps the problem simpler, actually. It seems like extra work, but it's actually usually simpler numbers. Okay, so what does 1/2 power mean? It means square root. So we square root the 3, and we square root the 4. And then 1 to anything is just 1. So at this point, can you recognize what your answer is? Distribute through the 2. This is where you have to know enough simplifying to be able to do this. So if I distribute through the 2, the negative 2, the 2's are going to cancel. Just get negative root 3. Negative 2 times negative 1 is positive 2.
Wait, how did the 1/2 on the 1 go away?
1 to anything is 1. So
Well, you still square root it?
I did. Square root of 1 is 1.
Oh, yeah.
1 to any power. It does not matter what we put up here. It's going to become a 1. And that's a good thing to just kind of know. It saves you from having to like waste time thinking about it. All right. The answer is E. That was a weird one. That's why I worked it out. I'm not working out all the weird ones. Some of them you're just going to have to do on your own. I am not